In this video, we're going to talk about proof by mathematical induction. One of my students asked me to put this up because they were having a little trouble in their discrete math class. So hope this is helpful. So let's start with function s of n equaling the sum of the first n positive integers. So in other words, it'll look something like 1 plus 2 plus 3 plus dot 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 plus n. And that is equal to s of n. So in other words, if we had, for example, s of 1, that's simply 1. We're just adding up the very first integer, the very first positive integer is 1. Not very instructive, but the starting point. S of 2, we're adding the first two positive integers, and that gives us 1 plus 2 equals 3. And let's go one more. S of 3, this is just to illustrate what this function looks like. S of 3 is 1 plus 2 plus 3, and that equals 6. In general, it's not obvious yet, but in general, we have the formula that S of n, which is 1 plus 2 plus 3 plus dot 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 plus n, is in fact equal to this formula, n times the quantity n plus 1 over 2. This is what we actually want to prove. We want to prove that the sum of the first n positive integers is equal to this nth integer, the last integer, times the next integer up, over 2. There are a lot of different ways that you can prove this, but this video will be focusing on a technique called proof by induction. So in order to prove by induction, there's two basic steps. The first is called the base case. That's our starting point. You need to show that the formula works for n equals 0 or for n equal 1. So in this case, what we need to do is we need to show s of could be 0 or 1 actually works in this formula. We'll do that in a second. The second case, or the second step rather, is called the inductive step. And in the inductive step, what you do is you assume the formula holds for n equals some arbitrary integer, let's call it k, some arbitrary positive integer k. And you need to show that it's true for n equal k plus 1. So let's consider this example, this particular function here, and see how it works in practice. So in other words, we want to prove that this formula gives us the sum of the first n integers. So our base case we need to show n equals 1 is true. Now we could start at n equals 0, you could start at n equals 5. The particular starting point is usually given in the context of the problem, and in this case we see that we're starting with the sum of 1 plus 2 plus 3. So our starting point is 1, which is why we're choosing n equal 1 as our base case. So that's simply showing that it's true for n equal 1. Well, s of 1, we want to see, does it work in this formula here? Is s of 1, which we know is 1, we know it's 1 because we've already shown it up here, but is this formula giving us the same answer? 1 times 1 plus 1 over 2. That does equal 1. This becomes 2. 2 over 2 is 1. 1 times 1 is 1. So this is a check. That works. Okay, so now the second step. This is called the inductive step. The inductive step. We're going to assume that n equals k is true. In other words, what that means is we are going to assume that s of k, which is 1 plus 2 plus 3 plus dot 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 up to k, is equal to the formula k times k plus 1 over 2. This is the important part. We're assuming this in fact holds. This is a formula we can use. We want to show, pick a different color here, show that n equals k plus 1 is also true. And what that means is we want to show that s of k plus 1, which is 1 plus 2 plus 3 plus dot 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 plus k plus the next positive integer up, which is k plus 1, that is equal to, that is equal to, now instead of k, we're going to say k plus 1, and then this is k plus 1 plus 1, or k plus 2, over 2. This is what we want to show. This is the part we want to show. So in order to show that, let's consider. So let's consider. S of k plus 1. Well, S of k plus 1 is equal to 1 plus 2 plus 3 plus dot 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 plus k plus k plus 1. That's just the straightforward definition of the function. Now, what we're going to use, however, is our n equals k plus 1 assumption right here. Comes out right here. 1 plus 2 plus 3 plus dot 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 plus k plus 1, plus k rather. That's equal to k times k plus 1 all over 2. That's what we're assuming true, so we can use that formula. So in other words, then we end up with this equaling k times k plus 1 over 2 plus k plus 1. Well, we want a common denominator, so k plus 1 over, we can write that over 2, but then we have to write a 2 parentheses k plus 1. So in other words, I wrote k plus 1 in terms of the common denominator of 2, but I introduced a factor of 2 in front of the numerator, so that all I did was rewrite k plus 1 as 2k plus 1 over 2, so I could get a common denominator. Now that common denominator, we can combine the numerators, so we have k parentheses k plus 1 plus 2 parentheses k plus 1 all over 2. All right, now the next step, so we're coming down here. If this k plus 1 and this k plus 1 are factors that appear in each term, k plus 1 and k plus 1 show up in each term in the numerator, I can factor out a k plus 1. So the k plus 1 is in the numerator expression on the left term as well as the right term. So I'm factoring out a k plus 1. And then what's left over in the first term is k, and in the second term is plus 2. So what's left over is k plus 2. All of that is divided by 2. Well, have we shown that s of k plus 1 is in fact equal to this formula? Well, that is exactly what we wanted to show. We wanted to show that in fact s of k plus 1 is equal to this formula, and we did. And if you realize the key here was showing that if we assume 1 plus 2 plus 3 plus all the way up to k is equal to this formula, if we assume that, then we were able to use this formula right here, where we have the 1 plus 2 plus 3 all the way up to plus k. We used that for the formula, and that was a key for helping us prove that s of k plus 1 is in fact this formula. So since the base case was proven to be true, or since the base case was true, and since the inductive step was proven to be true, we have proven by mathematical induction that in general s of n is equal to n times n plus 1 over 2. I hope this helps. Let me know if you have any questions. Thank you.